So my goals for this video are very simple. Let's say that I have a distillation column. I'll just draw, it's very odd. If I have some distillation column here, obviously to run it, I need some sort of set points. And to do that, okay, let's just move this here. And with those set points, I should be able to calculate theoretical outputs for the rest of my distillation column. So let's say that I have some givens here. So let's say I have some feed that's at a composition Z. So these are knowns. And coming out here on our distillate, I have some composition and I know the recovery. So this recovery term is analogous to kind of saying, I know I'm putting in some composition of this component in my feed. How much of that am I recovering in my distillate and how much of that am I recovering in my bottoms? So this is the recovery for our distillate. Now what I don't know yet, and I'll use a different color to demonstrate that. What I don't know is what's my distillate flow rate there. And then coming out the bottom, what's my bottom's flow rate and what's my bottom's composition. So these are things that are still unknown. So a very good starting place for starting to calculate some of these values is setting up a mass balance. So I'll start up top with our distillate because we have a little bit more information there. What I'm trying to find out is what this flow rate is. And the easiest way I can put this into an equation is saying, well, how much of my distillate am I actually flowing out of this component? And we can set this equal to basically saying, well, I have another flow rate, my feed flow rate. We can multiply that by the composition that I am interested in. But since not all of this is going to show up in our distillate, we account for the recovery that we actually get here at the top, which is a target value. So we have essentially set up a very simple mass balance for finding our distillate flow rate, because we know what the composition of our distillate is, we know our feed flow rate, we know the composition of our feed, and we know the recovery in our distillate. So we can then say our distillate is equal to Fz R sub D over X sub D. That's simple enough. What's almost even simpler is setting up an overall mass balance on our distillation column, which is to say that if we have some overall feed, that's equal to our exiting streams, which is our distillate and our bottoms. At this point, we now know our feed and our distillate because we're calculating that here. So all that's left to calculate for is our bottoms flow rate, which is simply our feed minus our distillate flow rate. Now the last thing that we can do, at this point, the only thing that we have left that we actually want to calculate, so we know this, all that's left is that bottoms composition. And we can work very similarly backwards. And what do I mean by that? If we start with this equation as a starting point, if we recognize that whatever wasn't recovered in the distillate is recovered in the bottoms, because if we're assuming a steady state ideal distillation column, then we recognize that whatever is recovered in our distillate plus whatever is recovered in our bottom has to be equal to 1, which is to say that our recovery in the bottoms is just 1 minus our recovery in the distillate. So let's work like with that assumption. So now we're going to do the feed times the composition times 1 minus the recovery of in the distillate. And instead of now calculating for the distillate, we're now looking at our bottom stream. So something like this is very similar to this initial equation that we had derived out of the mass balance. And now all we have left to do is calculate for our composition. So FZ 1 minus recovery distillate over B. And what we have now learned is that selection of our distillate composition and our distillate recovery is definitely crucial to the overall design and the outputs that we get in our distillation column. So that's pretty cool. And now given our values here, we can actually run along and calculate the rest of our desired outputs here. So now we're in a Python notebook. All this above here will help us do a bit more stuff with the McCabe-Thiele diagram. We're going to be calculating the operating lines and plotting them here as well. So that'll come a little bit later. What I do want to do here now is put in my inputs. So we said that we had defined the feed. We'll say that's like 1 mole per second. I'll put units here, mole per second. We want to define our feed composition. So maybe like 0.55. That's our composition. And we also want to define our distillate composition. So maybe 0.95, something like that. These are all just kind of theoretical values. You could always mess around with these a little bit to get better results. And then the last thing I'm going to put is our recovery in our distillate. So we'll say that's like a 90% recovery. Right? Now, what's left is incorporating these equations in there. So our first one, we'll go with our distillate. So let's pull that up. So we'll say our distillate is equal to our feed times our composition times recovery in the distillate over our distillate composition. If we do that, we see that our distillate flow rate is something like 0.52 moles per second. And now let's do our bottom. We'll do our bottoms. And since we've already calculated our distillate flow rate, we can just go ahead and write something down like this. So if we go for our B, that makes sense, because if we go now, our D plus B perfectly on the dot 1, which is what our feed is. So that makes a lot of sense. Now the last thing that we can actually calculate here is this last portion here, where we were kind of reverse engineering this mass balance to get an analogous situation for our bottoms. So let's go ahead and throw that into Python as well. So now we're calculating our composition in the bottoms. And we said that was our feed times our feed composition times 1 minus our D, our recovery in the distillate. And this is all over our bottoms flow rate. So now, if I look at what XB is, we see that whatever is coming out in the bottom, 11% of that is our liquid mole fraction. So that is a pretty easy, simple way to calculate these unknowns given these restraints. And that's pretty cool to see. So really quickly, I kind of want to go over how we can construct this kind of bare bones XY diagram, not using our bubble points and dew points, but rather using relative volatility. So this measure of relative volatility is something that we can use to relate our vapor composition to our liquid composition, and that's something that I've derived in the previous video. And that relationship looks something like this. So let me create just a set of, well, it's labeled X1, so I'll just follow suit. So let's create a set of linearly spaced x values. So we'll go from 0 to 1 because that is our maximum composition that we can have. You can't have anything more than 1. It is a ratio. And we'll put 20 evenly spaced points, something like that. So now if we look at x1s, boom, nice even space points. Now, the way we relate our y1s is using the relationship that looks like this. So our alpha times our x1s over 1 minus x1s plus alpha times x1s. So now if we look at our y1s, these are correlating to our x1s over here, and this will give us plots for our VLE diagram. So that's just a little quick crash course on how we are able to generate this graph. So let's start out with our rectifying line. We remember that from the operating line equation for a rectifying line, we have something that we define as a reflux ratio. And so right now we can set that reflux ratio to kind of be whatever we want. So I'm just going to choose 2 right now. And that's pretty much all we need to actually graph out this rectifying line. So let's go ahead and do that really quick. So I just used this autofill to kind of get me started here. So we remember from a previous derivation that when our x is equal to xd, our y is also equal to xd. So we have this one point where our x is equal to xd, maybe somewhere here. So this is one point. A second point can be chosen very conveniently if we set x equals to 0. So the second point that I'm going to put here is 0. Now, if I go back to my operating line equation, we can remember that that equation looks like r over r plus 1 times x. However, if x is equal to 0, what's left is our intercept, which is 1 over r plus 1 times xd, or xd over r plus 1. So our y, when x is equal to 0, is xd over r plus 1. I'm going to change this line color to maybe red. Oh, it's because I moved this stuff to up here. Just needed me to. But anyways, here we go. Remember, we set our distillate x to be 0.95. So that's exactly where that's starting. And our y is equal to our x distillate. So that looks great. And we're going all the way across to where this x equals 0. So I'd say that this is a pretty good rectifying line. So next, why don't we go ahead and we'll do the same thing for our Q line. So for the Q line, we need to add one more restraint, which is our feed quality. So we'll set that equal to 1. Let's say that we have saturated vapor. Why not? And it's a very similar process now. So we're going to add another scatter. Let's just let it autocomplete for us. Now, our starting Z is the composition over here, somewhere in the middle, something that we've already defined right there, 0.55. And we know that the same thing happens here. So that still falls on our x equals y line. And we're going to change this to Q. Now, if we remember from our equation for our Q line, that first term is Q over Q minus 1. And so if we were to set that x equal to 0, we now get Z over 1 minus Q, something like that. But now we will see a problem. Well, the first problem is that it doesn't see Q, but now the second problem is that we're getting a divide by 0 error. And that's because when we do 1 minus Q and we say Q equal to 1, that's Z over 0, which is undefined. a good way to get around this is either go to Q and go a billion zeros and then 1 at the very end just to add that infinitesimally small value, or we'll have Python do that for us. So what I can do is from this library here, so np.finfo, we get, I believe, np.float64. This is just a library, and from that I'm going to pull EPS, which stands for epsilon. And now if I look at what that is, you see we have this crazy small number. And this is essentially the smallest number that Python recognizes without round-off error. So if we actually add this EPS value, this epsilon value, at the very end here, whoa, that shouldn't be happening. But the reason that it goes all the way over here is because that's what we set our condition to. We said that we want this to end at x equals 0. Or rather, this is our second point that you need to find the slope and adjust for. But when we do that, we realize that this Q has a very, 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 very non-steep slope. It's almost vertical. So in order to get around that, we can pull a couple tricks here. So in order to do that, it's actually quite simple. We go into fig.updateAxes. So update axes. Well, we have to do them turn by turn, unfortunately. And we'll set a range. And this range is basically going to say, sure, something might be happening all the way back over there. We don't care about that. What we want to see is 0 to 1 only. And in fact, I don't even think we need to do that for the x-axis. I think we just do it for the y-axis, because that's the one we are worried about. So we're going to set that range, and there we go. I changed the color a little bit so you can see a little bit better against the blue. But it's exactly what we said. We added that infinitesimally small value to our q. So now that 1 minus q is actually 1 over a really, really, really small value. So we almost get an infinite slope. And that's exactly what we're seeing here. This nice vertical line that is representative of saturated liquid. So saturated liquid, of course, means that our feed quality is equal to 1. And this is the result that we get. Okay, so let's do this for our stripping line now. So remember that analogous to our reflux ratio for our rectifying section, we have something called a boil-up ratio for our stripping section. And in a previous video, we actually derived the equation for our boil-up ratio in terms of the reflux ratio, our distillate flow rate, our feed composition, and our feed quality. And that looked something like this. So we have R plus 1 times our distillate flow rate minus our feed times 1 minus Q. And this is all over our bottoms flow rate. And these are all things that we have defined beforehand. So all of these they are linked together. So one thing we could do now is we can take a look at newly calculated value. So we see right here that our boil-up ratio is quite high, and that's because our entire feed quality is saturated liquid. Well, what if I said that our entire feed was vapor, maybe slightly superheated vapor? Well, intuitively we think that, yeah, we should have to boil up less. That makes sense. So all of this is very intuitive. We'll go back to our original situation here. Okay. So now we can go ahead and add this last scatter for our stripping section. I'll let it finish some of it for me, but not all of it. So now we still have that one point where we have our x is equal to our bottom's x and our y is equal to our bottom's x. That lies somewhere down here on our x equals y line. However, we don't have the same luxury of sending that end bound to 0 anymore, because it never will touch x equals 0. It has to start at the bottoms and go up this way. And it'll intersect with this point here. So what we need to do is define some curve here on this vapor liquid equilibrium line, which we know how to do according to our operating line for our stripping equation, or for our stripping process rather. And the way we do that is, well, we'll set xb equal to, well, if we're up here, let's just say it goes to 1. That's fine. That slope that we have, or yeah, we'll push that all the way up to 1. That's fine. So we have now a VB plus 1 plus 1. And this will depend on the boil-up ratio here. Or sorry, we did VB plus X at the bottoms. That's another derivation that we've done. We did this in terms of just the boil-up ratio and our bottoms composition. That was all in a previous video. And then what we have here is just, believe, VB plus 1. And now if I run this, did I change? Oh. There we go, it's back to normal now. So now we see we have 3 intersecting lines. Where's bending? Yeah, right. We'll set this to yellow. Oh no. The name is stripping, and I want the color to be yellow. And there we go. So now we see we have our rectifying stripping Q lines. The last thing that we have to do is the little staircase that determines the number of theoretical trays that we have in our theoretical distillation column. So that will be your next and final step for completing this automatically generated McCabe-Thiele diagram. So now, the last thing that we have to do, or I guess the first step and the last thing that we have to do, is finding this point where all 3 of our operating lines intersect. And that's important, because as soon as our staircase crosses over this intersecting x value, we start basing our staircase off of our stripping line as opposed to our rectifying line. So go down to the rectifying, down to the rectifying, cross over, down to the stripping, down to the stripping, down to the stripping. So the way we can calculate that is, this is the whiteboard that we had used last time to derive all of our equations that we were using for this code actually. We use this equation to find this intersecting x value. And we'll use that as our boundary for crossing over into the other regime of our distillation column. So let's just code that out. So I'll name this something like x-intercept, something like that. First thing that we got, z over q minus 1. So z over q minus 1, not x. Right? And then from this, we're going to subtract, no, we're going to add, sorry. xd over r plus 1. That exactly. And then this is all over so q over q minus 1 and minus r over r plus 1. Hopefully my parentheses are all right. And then maybe a little more right here. Aha. So we're getting that same thing down here because of that little epsilon, right? So we're going to add that on here. And I think we could just go EPS plus. And then say here EPS plus. Cool. So Python has now stored a value. And now let's see if that value actually lines up. So 0.55 is what it's telling us. And if we follow this down to our intersecting point, hopefully it lets me. Right, so we have a vertical line. This goes up into our intersection, and it says that it's at 0.55. This is at 0.55, some really tiny number, probably because of this epsilon. So that's close enough in my book. So now we can start actually plotting out our staircase now that we know our crossover point. So before we move on, I kind of want to think about our strategy here. So in order to generate these stairs, we first off do understand that we're going to have to create some sort of for loop because we want to keep using a sort of iterative calculation to get us our staircase. The issue with that is that we start over here at our x equals y line. Our first step is going to be crossing over to our vapor liquid equilibrium line upon the same y value, upon y equals 0.95. But we do understand that our x is going to change. So how do we calculate this VLE curve? We actually calculated it using this equation here. And so going backwards, we can actually do the same thing, calculating out for our x's using our y's and the relative volatility. So let me write this out. What we have right now is something that looks like this. So first, let me multiply this denominator out. So y minus xy plus axy, alpha xi rather, equals to alpha x. Then I'm going to gather all my x terms on one side. So actually, how do I want to do that? Yeah, let me gather all my x terms on one side. How's that? So alpha x plus xy minus alpha xy equals y. Factor out my x equals x times alpha plus y plus alpha y minus alpha y. Here we go. So this actually looks very similar. It's just that now we've kind of reversed this sign and reversed this sign. Y over alpha plus y minus alpha y. So we can then use that to calculate our x's. So let's go ahead and see what that looks like. Let me throw in another section here. And let me create some new lists. So I'm going to name this my x steps. And we'll initiate this array with our initial value, which is xd. And then we'll initiate our y steps array equal to xd as well, of course. Then what we need is an initial value of y. So I'm just going to have that be our initial value in our array. And I'll have that be position 1. So when I do that, actually what ends up happening, or 0, because of Python's numbering system. So when I do that, y is equal to 0.95, which is xd, which is defined right there. If I were to change that, it would change everything. So just making sure all this stays automatic. So now I'm going to say something like for a counter I in some range, stick with 100 for now, why not? So what we want to do is we want to bring in the x value that correlates with our y value. So x equals y over it's alpha plus y minus alpha y. So a plus y plus, or minus, right? Yeah, minus alpha times y. Okay. So let's see what that first x is. So looks something like this. So just a little bit lower, and that actually doesn't look too bad, I don't believe. If this is at 0.9, it's a little bit lower if we go. So yeah, about that range. So let's continue on with this now. Now essentially what we're going to end up doing is we are going to append this x value into our list. So it's going to be steps dot append, and we're going to append each x value, and then we're going to want to do the same for the y value. And then we're going to append the y there. Right? So now if we want to take a look at our two arrays, okay, right now it's just doing it over and over and over again. But once we actually start doing the recurring calculations, it'll change these values little by little. So we'll be able to actually grab solid data for that. So let's go ahead and code that out. So now, yes, we have this loop, but we also probably want to throw in some conditionals. And the most obvious conditional that we have is, well, when should we stop? And that's easy enough. We don't want to go any lower than this x value here that relates to our x of the bottom. So that bottom composition, there's no point in going any lower than that because we're not going to be operating lower than that. So we could say if x less than xb, right? We can just say we're done. Just break. That's a pretty easy argument to make. So if we ever go lower than that, stop the count. Else, we want to probably check another well, actually, I don't think we need an else here. I think we just go in and do another conditional. So the next conditional that we might want to have is our crossover point. So this point here. So now we say if x is greater than or equal, actually, I believe we want it to be less than, right? Yeah, we want x to be less than that. Is less than or equal to x int. Then we want to switch to our stripping operating line, which looks like, well, we could do it both ways. We could say that if x is less than our intercept, then we want to switch to our stripping line. But I think since we're already starting in the rectifying section, what might make more sense is to say if we are greater then this intercept, if we are still in our rectifying section, use our rectifying operating line. So we'll say y is equal to r over r plus 1 times x plus our x distillate over r plus 1. But if we are not meeting that condition, so we hit this else, then we switch to our stripping operating line, which looks like VB, so VB times, VB over VB, no, sorry, plus 1 over VB times x plus our x bottoms over VB. Did I say that right? Believe so. I just got to put extra parentheses here probably. Just check that let's just check that if x equals xb, x equals xb, this there. No, so this should be minus here. So that fits. All right. And I think that's probably it. So now we can maybe take a look at our, I'm going to put these at the very end. Okay, do that. Now let's look at our x steps. I don't know why it only did it twice. Okay, I think it just needed a bit more parentheses here. And now we actually have a set for our x and our y. So that's great. Let's add this. Let's add this on. Add scatter. So we want to plot an array of x's and then an array of y's. So I think what we can do is go x is equal to x underscore steps, y is equal to y underscore steps. Let's just see what this does. Okay. So it seems to only be plotting on the line when we really want it to go across and then plot it. So I wonder if changing this actually messed something up. What does that look like here? Okay, now it's just following our equilibrium curve. Okay, so I just made sure to have the append on both ends because you need to kind of double count them a little bit. And it seems that we actually have solid values. I think what might have happened is that if we only append one at the beginning and then one at the end, it actually only applies to each line. So if we put it at the top, it's only going to follow our VLE line. If we only put it at the bottom, it's only going to follow our operation lines. So having them on the top and the bottom actually allows us to have that staircasing jumping from operating to VLE to operating to VLE. And I think now, there we go. We have a nice, beautiful staircase. I don't like that there are little pointers there. So I'm actually going to set this mode equal to lines. And we see this nice, beautiful staircase. We jump over that crossover point and we keep going. And we see that this last little leg here, this actually doesn't perfectly line up with our bottom's composition. This little segment that branches off here is actually for a reboiler. So is kind of why it's branching off like that. It's kind of just kind of like saying like, we got close enough, there's not much else we can do. But this is how that staircase is generated. So very, very happy with that. So the last thing that we can actually do here is we can actually experiment a little bit with this graph by changing our reflux ratio. Where is it? So right now we have it set to 2. If we set it to something like 0.8, let's say, we see that we actually never make it out of this rectifying section. It gets way too narrow, and then it actually never crosses over into our stripping section, which is why the reflux ratio is actually incredibly important for sizing a distillation column. So let's do 1.5. This is looking a lot better. You see that we actually have that nice staircasing that branches out over into our stripping section. But let's say if we had a really big reflux ratio, so like 5. All right. So now we see that we actually have much larger steps here. So we're refluxing a lot more. We're forcing a lot more liquid down in through our distillation column. We get these much bigger steps. And the rectifying and stripping lines become more closely aligned to that x equals y line. So this actually might not even produce that well of a product in the end. So really sizing this distillation column using the reflux ratio is really quite important. But that is everything to cover in this video. We have gone through the calculations necessary to plot a McCabe-Thiele diagram. We have gone through this degrees of freedom analysis using mass balances to allow us to calculate unknowns using only a handful of inputs. And we have demonstrated how we can construct the McCabe-Thiele method and how we can adjust the step sizing using our reflux ratio.